to speak here, and also it is very nice I can come back here in class. Thank you for the organizer, especially to Professor Adachi. Thank you. Today, I would like to talk about asymptotic behavior of trajectory on Hadamard Kähler manifold. Hadamard Kähler manifold is a simply connected Kähler manifold of nonpositive sectional curvatures. It is needless to say that the study of geodesics is one of the main subjects in Riemannian geometry. For example, variation of geodesics shows conjugate points and focal points, and considering geodesic triangles, we have famous Toponogov's comparison theorem. And from the viewpoint of submanifold theory, considering the extrinsic shape of geodesics, we can give some characterization. For example, we have an old result of Nomiziano. But now, I'd like to show my motivation. We consider a family of curves. If we consider a big family, extended family concerning including geodesics, can we say what properties on the underlying manifold, especially if the family is closely related with the geometric structure. So, we here need to introduce some suitable curves. From the viewpoint of Rene-Serre formula, circles which satisfies these equations is the most simplest curve next to geodesics. As I said before, circles are used to study submanifolds. For example, the characterization of extrinsic sphere, and also there is many results on isometric embeddings by using extrinsic shape of circles from the ambient space. But as you can easily see, that to use circles, we need initial conditions, velocity vector and acceleration vectors. So, from the viewpoint of dynamical system, circles are not easy to treat. From the dynamical point of view, as geodesic determines the geodesic flow on the unit tangent bundle, I hope the family induces the perturbation of geodesic flow. Now, I use the terminology. A closed two-form on a Riemannian manifold is said to be a magnetic field. For magnetic field, yesterday Professor Muntenu explained very nice, give a very nice lecture, so maybe I do not need to explain anymore. But the reason why we use, we say magnetic field is because it is natural extension of the static magnetic field on the Euclidean 3 space. We here give two examples. One is the Kähler form of the Kähler manifold. We use this signature, Professor Montiani's signatures is different from me. We need minus, but it is not the matter. And we call the constant multiple of this scalar form the Kähler magnetic field. Another example is on the almost contact metric structure without some additional conditions such as a Sakian manifold, or it is a real hypersurface of a Kähler manifold. The fundamental form, which corresponds to the Kähler form, is closed. So the constant multiple of this form is said to be a contact magnetic field. We have two works because for given the magnetic field, its trajectory is, we studied the property of trajectories. Yesterday's talk was concerning this magnetic field. And today, I'd like to concern Kähler magnetic field. Here, given the Kähler manifold, we take Kähler magnetic field, which is a constant multiple of the Kähler form. A smooth curve parameterized by its arc length is said to be a trajectory or a magnetic curve for this Kähler magnetic field if it satisfies these equations. Yesterday, Professor Montiani said when it is parameterized by arc length, it is set normal. But as I only treat the normal trajectories, so I just say trajectories. When kappa is 0, trajectories are geodesics. Moreover, for trajectory for Kähler magnetic field are circles because the complex structure J is parallel. So we have this equation. Hence, the trajectory is a kind of circle. Moreover, so given the unit tangent vector, we denote by gamma u the trajectory of for Kähler magnetic field with initial vector u. So this is a trajectory, and just like we define the geodesic flow, we can define magnetic flow by this. Of course, when kappa equals 0, the magnetic flow is the geodesic flow. So the family of magnetic flows is a perturbation of the geodesic flow. So from both viewpoint, from the Fresnel formula, Kähler trajectory is a circle, so it is good. And from the viewpoint of dynamical system, we can introduce magnetic flow. So I think this is very interesting object. But though I use the term of physics, the principal part of generating operator is Laplacian, not the shredding operator. For example, we consider a spherical mean, that is taking the average of the magnetic sphere of radius of trajectory length of r. We define this spherical mean. Then its expansion is of this form. And the principal part is Laplacian, and the influence of the magnetic field appears this point. So the fourth order, only fourth order. Now, I'd like to recall the feature of trajectory on the complex space form. I'm sorry, this was also explained by Professor Mutanu. But this is a very key point I'd like to explain. I explain again. On the complex projective space of constant holomorphic sectional curvature C, every trajectory is closed of length 2 pi over square root of kappa squared plus C. The feature is this. And all Kähler magnetic flows are conjugate with each other. This means that there is a diffeomorphism Fk on the unit tangent bundle satisfying this relation. So changing the speed, this is a geodesic flow, so magnetic flow is equivalent to conjugate to the geodesic flows. Of course, on a Euclidean space, every trajectory except the geodesic is closed, and except the geodesic flow, they are conjugate with each other. So we like to explain on the feature on the complex hyperbolic space. To do this, we need introduce some terminologies. On the, let M be a Hadamard manifold. As we say, it is a simply connected Riemannian manifold of non-positive sectional curvature. Then we can define its ideal boundary, M infinity I denote. This ideal boundary is a set of all asymptotic classes of geodesic rays of unit speed. And the union, on the union of M and M infinity, we introduce the cone topology. The image of the open basis at the infinity point is like this figure. With this topology, this M bar is compact. Actually, we have this is a Poincaré model of complex hyperbolic space. This circle in the inside. And the topological boundary of this Poincaré ball coincides with the ideal boundary, and the topology is the same. So we say a curve gamma on a Hadamard manifold is unbounded in both directions if both of the set gamma minus infinity to 0 and gamma 0 to infinity are unbounded. In this case, we set gamma infinity and gamma minus infinity as the limit of this curve in the ideal boundary and call them the limit point of gamma. Now, we take a trajectory for Kähler magnetic field B kappa on the complex hyperbolic space. Then, when kappa is greater than the square root of the absolute value of the constant holomorphic sectional curvature, it is bounded, moreover, it is closed. When the absolute value of kappa is less than this value, it has two distinct limit points. The blue one, this is a case when kappa, the second case, oh, this is a third, sorry. And when equality holds, this is a green one, it has single limit point. It is said to be horocycle. And corresponding to this, Kähler magnetic flows are classified into 3 conjugate classes. like geodesic flow, horocycle flow, and rotation flow. And maybe you remember the first lecture on the Poincare disks. You have the geodesics closest to the ideal boundary orthogonally, and on Poincare disk, every two distinct points you can join them by geodesic. On the other hand, if we compactify Euclidean space, only antipolar point can be joined by geodesics. So, Euclidean case, the geodesic is very characterized, I think characterized, and how about complex hyperbolic space of constant holomorphic sectional curvature C? I hope the green trajectory characterizes this. We here pose a question. On the general Hadamard Kähler manifold, how trajectory behaves? Existence of horocycle trajectory shows something. If we give some condition on curvature, sectional curvature is mostly hard conditions from above or from below. We study these problems by preparing comparison theorem corresponding to Toponogov's theorems. As a correspondence of geodesic triangles, we use trajectory and geodesics. Let gamma be a trajectory segment or ray for a Kähler magnetic field. We suppose gamma t does not come back to the origin. We say a variation of geodesics a trajectory half associated with gamma if it is a smooth map and satisfies these three conditions. Every geodesic starts with the origin of the trajectory when the t equals 0, the geodesic is a tangent line, and when positive t, the geodesic joins origin and the point gamma t. We note when we consider Hadamard manifold, we do not need this remark, but generally, when the image lies in the ball of radius of minimum conjugate value of gamma 0 of the origin, we can define trajectory half under the assumption of this. So, to measure this trajectory half, we here introduce some quantities. For trajectory half, we set L gamma, the length of origin and between here, the length L. And the delta is the inner product of the velocity vector of gamma and the velocity vector of geodesics. And eta is the same inner product of here. We shall call them string length, string cosine, and string elevations. By direct computation, the differential of string length coincides with the string cosine. Here, we give example. On the complex Euclidean space, the string length, this is I forgot how to say in English, but here. So it gives like this. And string cosine and string elevation, and this is the same. So you can check this. Elementary Euclidean geometry. So they are given like this. On a complex hyperbolic space, we can write these quantities like this. Of course, it is not easy to understand at this moment, but important thing is when this 0t pi over square kappa square plus c, I denote this for all the cases c is positive, 0 and negative. So we regard this quantity as infinity when the complex hyperbolic space with kappa is small. And then the string length is monotone increasing, and the string cosine is monotone decreasing. This means that on the complex hyperbolic space, when the strength of magnetic field is small, the string length is unbounded. Now, I'd like to give some comparison result. Since the string length of the for complex space form is monotone increasing, we denote its inverse function by tau kappa. We call this red part the half body at T naught. This is a comparison theorem. For trajectory half, if the sectional curvature tangent to the half body is less than c, then the string length is greater and not smaller than the string length of constant holomorphic sectional curvature. This is, you can see like this, and the string cosine is greater. Please note that we do not compare this part and not this part and not this part. We compare this part and this part. This point is very important. In these cases, if the equality holds as some T naught, then the half body is totally geodesic, totally complex, and constant sectional curvature. So I think this the trajectory can be written by this, by using trajectory half. We can give a norm of Jacobi field like this by using the string cosine, and the differential of string cosine can be expressed like this. So the first part is we can understand this figure satisfy this, and the second part is expressed by using this. So this part can be estimated by Lauch's comparison theorem. So we can get our comparison theorem through Lauch's comparison theorem. In order to measure, in order to show that the trajectory goes infinity and have limit point, we need another quantities. Given the trajectory half, we consider this red part, and we say this red part half sector. And we call this curve is a sector arc, and this curve in the unit tangent space, we call this zenith angle. Zenith angle is closely related to the string elevation. But you can easily see that you can calculate, you can give an estimate like this. Then, the string, we have such expression on these quantities on complex space form. So, we can give an estimate like this. So, given the half sector, we compare half sector and half sector on the constant complex space form. The point is, we need to take the same length position. Then we can compare these. This is because these quantities can be written like such. This is a norm of a Jacobi field, and this is a norm of the derivative of Jacobi field at the origin. So we can give an estimate by using a Rouse's comparison theorem. So we give asymptotic behavior. If a trajectory ray for B kappa satisfies this sectional curvature condition, this means the sectional curvature tangent to the half body is not greater than minus kappa square, kappa and kappa square. Then by using the comparison theorem on string length, this trajectory rays is unbounded. Also, by using the comparison theorem on the zenith angle, we can give us the limit of the initial vector of geodesics exists. So we can get the limit geodesics. We call the limit geodesic the limit string of this trajectory half. Of course, the limit point of trajectory coincide with the limit string, the limit point of the limit strings. So now we give the case, horocycle case. On the Hadamard manifold, a smooth curve parameterized by its arc length is said to be horocyclic if it satisfies the following two conditions. It is bounded in both directions, this blue line, both directions. If it crosses to a geodesic sigma, the dotted line, with having the same limit point, they cross orthogonally. So if this condition is satisfied, we call this gamma horocyclic. And also, as half body is only for trajectory rays, for this trajectory rays, and also we have trajectories, inverse trajectory rays. So the union, we say the union, the total half body. If a trajectory for a Kähler magnetic field on Hadamard Kähler manifold satisfies the sectional curvature of tangent to the total half body is not greater than minus kappa square, and the limit, we have single limit point, then this trajectory is horocyclic, and the initial vector of limit string is the J-term velocity vector. And the total hyperbolic is totally geodesic, totally complex, and constant sectional curvatures. This is the consequence of comparison theorem on string elevations. I think maybe you consider the condition, our condition is very strong, I think. You consider our condition is very strong, maybe. But you remember, on the complete non-compact Riemannian manifold, a geodesic of unit speed is said to be a line if it satisfies the distance between sigma t1 and sigma t2 coincide with the distance in the Euclidean real line. By using such the existence of real line, we can define Boltzmann function and get a splitting theorem under the assumption which curvature is non-negative. And corresponding to this, we say that a trajectory gamma for Kähler magnetic field on a non-compact Kähler manifold to be, is accurate if it satisfies the distance between 2 points coincide with string lengths of constant holomorphic sectional curvature. Then we suppose that Kähler manifold, this non-compact Kähler manifold satisfy this condition. Sectional curvature is bounded from below, not from above, from below. If we have an accurate trajectory gamma for this magnetic field, then its total half body is totally geodesic, totally complex, and constant sectional curvature. I hope this corresponds to the partially this point. I think it is better to stop here. So.